Retrosynthesis with aromatic compounds. So we're going to conclude this chapter by looking at some organic synthesis examples. And at the end of this lesson, we're going to go through 6 different examples, and we'll show you how to work them out and things you should consider. But before we get there, we're really going to take a look at several common patterns you're going to want to be familiar with before you start attempting these retrosynthesis problems. Now, this lesson's part of my organic chemistry playlist. I'm releasing them weekly throughout the school year, so if you want to be notified every time I post a new lesson, subscribe to the channel and click the bell notification. All right, so everything we're going to look at with these patterns are things we've brought up somewhere along the way. I just want them at the forefront of your mind before we start attempting some of these retrosynthesis problems. So the first here, I've got a strongly deactivated benzene ring having this strong electron withdrawing group attached to it, and strongly deactivated again from an EAS perspective. And here I'm trying to do Friedel-Crafts alkylation, here I'm trying to do Friedel-Crafts acylation, and you should recall that both Friedel-Crafts reactions are not possible for strongly deactivated rings. And so if I've got something like a nitro group or a cyano group or a sulfonate group, any of those strong electron withdrawing groups, not going to happen. If it has a carbonyl, like a ketone attached, where the carbonyl is the adjacent carbon, so ketone, aldehyde, carboxylic acid, ester, whatever, those aren't going to work either. However, if I've got just simply a halogen like a fluorine, chlorine, bromine, iodine, those are still slightly deactivated with those weak electron withdrawing groups, but that is actually the bare minimum of what's allowed to react in a Friedel-Crafts. So with just a halogen, you can do this, but with any of the moderate or strong electron withdrawing groups, that's when Friedel-Crafts reactions are shut down. And again, as a reminder, it's just the 2 Friedel-Crafts reactions that you can't do, Friedel-Crafts alkylation and acylation. All the other EAS reactions would be possible. So you could do, nitration, sulfonation, bromination, chlorination, just not Friedel-Crafts. All right, so the next pattern I'm going to look at is when you do substitution at the ortho position alone. So in this case, I've got ethyl benzene, and he's a nice ortho para director. So however, I've attached an acyl group, which would go on through a Friedel-Crafts acylation. However, I've attached it at the ortho position and not at the para. And we learned Friedel-Crafts acylation. We said if you've got an ortho para director attached, it's much more likely to go para than ortho just due to the size. So how can I make sure it only goes ortho and not para? Well, it turns out it's through sulfonation. So first thing we're going to do here is add fuming sulfuric acid, SO3, and concentrated H2SO4. And in this case, it's going to add that bulky sulfonate group, and the ethyl group is going to direct it to either the ortho or para positions, but because of its bulkiness, it's only largely going to go para. Cool, so that's that lovely sulfonate group. And what's nice, as you recall, is this is totally reversible. I can use dilute sulfuric acid to take it and remove it right back off. So, but while it's there, now we can do Friedel-Crafts acylation. So, and in this case, because, the para is taken, it's only the orthos that are available. So again, he's an ortho para director. He says, I prefer these 2 positions. He's a meta director. He says, I also prefer those 2 positions. So there's no disagreement here. Had there been a disagreement, though, our lovely donating group would have been the deciding factor. So, but in this case, whether I go here or here, it's the same thing. This thing is symmetrical. Cool, taking us right here. And now, because we temporarily blocked that para position, we've got our lovely acylation occurring in the proper position, and now we'll just desulfonate with our dilute H2SO4. So once again, if you've got an ortho para director and you want to only go ortho, this is one way to pull it off selectively using that lovely sulfonate group as a blocker of that para position. All right, so last patterns I want to look at are what I'm going to call crossover reactions, and nobody calls them that. That's just my little name. So, but it's where you can turn a meta director into an ortho para director or vice versa, which gives you some options of where your EAS reactions could take place. And so the first one I'll take a look at is we're going to do Friedel-Crafts alkylation here. And if we do Friedel-Crafts alkylation, we add that lovely ethyl group, and that ethyl group's an ortho para director. So if we were to do an EAS right now, the electrophile would add either at the ortho or para positions or both in that case. So however, what I want to focus on is what else you could do with this ethyl group is you could take chromic acid or potassium permanganate which would cleave off one carbon here, as you might recall. So our benzylic carbon definitely has hydrogen, so this reaction will work. We'll cleave off any additional carbons besides the benzylic carbon, and then oxidize that benzylic carbon to a carboxylic acid. And so the big thing here is that the ethyl group was an ortho para director, but our carboxylic acid here, with the carbonyl being the carbon directly attached, that is a meta director. And so if I do if I do an EAS reaction before the side chain oxidation here, well then my electrophile is going to end up either ortho or para relative to the ethyl group. So, however, if I do it after side chain oxidation, well then my electrophile would end up meta to the carboxylic acid instead. And so it gives me some options. I just have to adjust when I'm doing an EAS reaction, either before or after the side chain oxidation. We'll see something similar in the second pattern here, and we're going to start off by doing a Friedel-Crafts acylation. So there's our acyl group added. And again, this acyl group right here with the carbonyl carbon being directly attached to the ring, this is a meta director. And if we were to do an EAS reaction now, it would add either this meta position here or this meta position here. They'd be equivalent in every respect. So, however, we also learned how to reduce an acyl group, like say with the Clemenson reduction. So, and we reduce it to an ethyl group here, complete deoxygenation, and that alkyl group is an ortho para director. And so if we waited to do EAS now the new electrophile would end up ortho or para relative. And so we've got options again. Either I can do EAS before the final side chain reduction, or I can do it after the final side chain reduction and get different regioisomers as a result. All right, one more here, and this one we're going to start off with nitration. So in this case, we're going to add that nitro group, and that nitro group, being a strong electron withdrawing group, is a meta director. So however, we learned how to reduce that nitro group, and we could do catalytic hydrogenation to pull it off, the general reduction, or we could do the specific reduction and use like zinc, tin, or iron, along with hydrochloric acid, followed by hydroxide to neutralize. And you could reduce that nitro group to an amine, in this case making aniline. And now that would be an ortho para director. And so the question is, you've got options of when you want to do your EAS reaction. Do you want to do EAS before your final reduction? Well, then right then you'd have a meta director, and you'd end up with your electrophile in one of the two meta positions. But if you do EAS after the side chain reduction, now he's an ortho para director, and so your new electrophile would end up either at the ortho or para or both positions. And so different regioisomers are possible. So all of these reactions can lead to different possible regioisomers, and you just want to keep these in mind as you're approaching your retrosynthesis problems with aromatic compounds. Let's take a look at some examples. All right, so for our first retrosynthesis example, we're going to convert benzene into this lovely di-substituted benzene. And the way you want to approach this is you want to look over at your structure here, especially when you're starting from benzene with no substituents, and you want to say, okay, I've got to add these two substituents. If, let's say, I added the sulfonate group first, so I'll cover up the ethyl group. If I added the sulfonate group first, where would it direct the second substituent to go? Well, he's a meta director, so it would direct it either to this position or this position, which is definitely not where we want the second substituent to end up. So we probably don't want to put him on first. Now, if we put the ethyl group on first, so he's an ortho para director, and so would he direct the sulfonate group to go in the right location? Well, in this case, ortho and para is one of the locations, and due to the bulkiness, that's where a sulfonate group would end up anyways. And so what we've just realized is that we want to do the ethyl group first and the sulfonate group second to make this work out properly. So second thing you want to look at is like, well, how do I add an ethyl group and how do I add a sulfonate group? And with your ethyl group, you'd be like, oh, that's an alkyl group. That's Friedel-Crafts alkylation. So, and with your sulfonate group, that's just sulfonation. So we definitely two of your standard reactions, not a lot of trickery in making those here. So first step to add that ethyl group. Friedel-Crafts alkylation. And then to add the sulfonate group, fuming sulfuric acid. And like I said, ethyl group is an ortho para director, but with the sulfonate being such a large group, it predominantly goes para, leading us to our final product. So Cool, started us off with a simpler example. These are going to get progressively harder as we go along. Let's take a look at another one. So in this next one, we're starting off with pure benzene again. We're also ending up with a disubstituted benzene, and we'll take a similar approach here and we'll say, okay, well, if you've got the carboxylic acid there first, where would it do the directing? Well, he's a meta-director, and so he'd direct either here or here, and that's one of the right positions. Okay, so far so good. But what if we added the nitro group first? What kind of director is he? Well, he's also a meta-director, and he would direct whatever comes on next, either here or here. And so it looks like in principle you could do this either way. So however, you can't. So if you look at that carboxylic acid, we've got to attach a carbon, and to attach a carbon, so you can't just add a carboxylic acid onto a benzene. We don't have an EAS reaction for that. We can add either an alkyl group or an acyl group, Friedel-Crafts alkylation or Friedel-Crafts acylation. And the thing we should always keep in mind was that first set of patterns we learned that you can't do Friedel-Crafts reactions on a heavily deactivated ring. So if we had the nitro group first, we wouldn't be able to do Friedel-Crafts after that. So this can't go first. This is going to have to go second. And so in this case, it's the carboxylic acid that's going to have to go first, but we can't do that in one step. We have to do a Friedel-Crafts reaction first, and then you've learned how to do side chain oxidation with either potassium permanganate or chromic acid after the alkylation. So in this case, I like starting with 2 carbons. You technically could do this with like methyl chloride and AlCl3. So although the likelihood of forming a methyl carbocation and stuff like this, it's not the greatest combination. Some people don't have a problem with it, and some professors, and some like, oh, you actually can't use the methyl. Whoa. So I don't know which direction you've gotten. So, but I just try to avoid using methyl chloride for that reason, but you'll find it commonly purported in many textbooks and by many professors. So, but in this case, I did it with an ethyl. As long as we have got benzylic hydrogens, it wouldn't matter which one we used. Now, in this case, we've also got a crossover that's possible. I could do the nitration, the EAS nitration, before or after oxidation. And the question is, would it make a difference? Well, yeah, it would make a difference, because if I do it now, that nitro group's going to either end up ortho or para, with the alkyl group being an ortho-para director. Well, then I don't want to do it now. So we should do the oxidation first. And again, potassium permanganate or chromic acid, and chromic acid is shorter to write, which is why I usually do it that way. So that gets us our carboxylic acid, and then from there, that carboxylic acid is indeed a meta-director, and we can do the nitration with mixed acid, HNO3, H2SO4, and there's our complete retrosynthesis. All right, our next example here, again, we're starting with plain old benzene, and we're ending up with yet another disubstituted benzene ring. So we'll kind of take a similar approach here, and we'll say, well, if we added the ethyl group first, where would it direct things to go? Well, it would direct things to the ortho and para positions, and we do want an ortho, so that's possible. What if we added the nitro group first? Well, he'd be a meta-director, and he'd direct towards either one of these positions, not to the one we need. So we know that the nitro can't be first. Can't be first. So, but we got something else to remember too, and it's one of our common patterns. In this case, we don't want the para, we just want the ortho. And we had a way of blocking the para position to accomplish that. So definitely the first thing we want to do is get that ethyl group on there, but before we add the nitro, we'll need to block. And so in this case, adding that carbon chain is just Friedel-Crafts alkylation. Good to go there. If we did nitration now, we'd form both the ortho and para. So, and probably more of the para, truth be told, than the ortho. And so if we want just the ortho, we really best route to go is blocking that para position with sulfonation. So add the big bulky sulfonation group, and now we can actually do the nitration. Whether we add it to this ortho position or this one, it does not matter, but the ethyl group would be the one getting to do the directing. And then finally, we could desulfonate here with dilute sulfuric acid. Cool, and there we go, one of our common patterns. Let's take a look at another. So in this next example, we'll start with plain old benzene again, and once again, ending up with a di-substituted benzene ring. We'll take the same approach here. So if we had the carboxylic acid first, where would it direct the next thing to go? Well, he's a electron withdrawing group and a meta director. Well, we don't want to substitute at the meta position, we want to substitute at the para position, so we'd come to the conclusion that he shouldn't be first. Problem is then we go to the other side and say, okay, well, let's cover that guy up and look at the nitro group as being added first, and where would he direct things to go? Well, in this case, he's also a meta director, and he'd direct things to the meta position, and that's not where we want to substitute either. So now we have a problem. You're like, well, then neither one can go first, and that makes no sense. So, but when you come to this kind of a situation, you're going to use one of those crossover reactions. Again, that's my personal term for them. So where something either goes from an orthopara director to a meta, or from a meta to orthopara somewhere along the way, and you can decide to do EAS before or after the change. And so in this case, you got to look and say, okay, well, how do you put these things on there to begin with? Well, the nitro group, we just do nitration, HNO3, H2SO4. So, but the carboxylic acid, again, we can't do that in a single step. So if you're adding a carbon, you got to do a Friedel-Crafts reaction. And if you want to end up with a carboxylic acid, then you have to do side chain oxidation afterwards. So in this case, we could do Friedel-Crafts alkylation, and put an alkyl group in that position, and then oxidize it as well. But the key is, when we put the alkyl group on, for a brief moment, that's going to be an orthopara director, and then when we oxidize it and turn it into a carboxylic acid, it'll then be a meta director. Well, because I want something in that para position, that's what we're going to take advantage of when we add that alkyl group. So the other thing to keep in mind is that we've got a nitro group there. If the only way to add a carbon is through one of the Friedel-Crafts reactions, then you couldn't do this second anyways. You couldn't do the nitro first because you'd have a strongly deactivated benzene, and you couldn't do Friedel-Crafts afterward anyways. So we got to do Friedel-Crafts first regardless. Cool, and like I said, we're going to do side chain oxidation in a minute, but for a second here, we've got an ortho-para director, and we want a nitro group to end up para, and so before we oxidize this and turn it into a carboxylic acid, which would be a meta director, we better do our EAS reaction first. And so in this case, we'll do HNO3, H2SO4. And so we'll get the para product, truth be told, will probably predominate, most undoubtedly. It turns out when you've got an orthopara director, most of the EAS reactions will end up being para preferred. However, you're still probably going to get some ortho in there as well. And so most of the time, professors want you to predict both. And so when this comes up in a synthesis problem, one way I've seen professors handle this is they have you show both of these, but then they have you write separate isomers. And so even though this would be the major product and this would be the minor, before you proceed on with your synthesis, you'd have to do some form of purification, like run a column or something like this. And you'd purify out just the para isomer and then continue on the synthesis with just that para isomer. In this case, we need to do our side chain oxidation, which once again, I prefer using chromic acid, but you could use potassium permanganate, and that would again cleave off any carbons besides the benzylic one from the side chain, and then completely oxidize it to a carboxylic acid, and voila. So hopefully you're noticing the trend here. We got another synthesis, and we're starting with plain old benzene and ending up yet again with a di-substituted benzene ring here. And we'll take the same approach, and we'll say if the ethyl group was attached first, well, he's an ortho-para director, and he would direct whatever electrophile comes next in the ortho or para positions, but we actually want this on the meta, okay? So we'd probably conclude that he shouldn't be first, but then we go over here and put the bromine on, and again, he's electron withdrawing and deactivating, but he's still an ortho-para director, and he would direct the next electrophile to go on ortho or para, which is again not where we want it. And when you come across this scenario, you got to think of one of those crossovers and figure out how to get there. Now, to put a bromine on, we've only really learned one way to put the bromine on the ring, and you just do it Br2 FeBr3 and Friedel-Crafts EAS bromination. I keep saying Friedel-Crafts EAS bromination, and that's it. Now it turns out there are other ways to do it, but we haven't presented them in this chapter. Some books do, so if you've got one of those, well, maybe you've got some other options, but for what we've presented in this chapter, we don't. There's one way to do this, but for the alkyl group, we've got really two options. You can do it in one step with a Friedel-Crafts alkylation, but if we do, we have no way to make this. But you can do it in two steps as well. You can do the Friedel-Crafts acylation first and then do side chain reduction. And what's nice is if you do the Friedel-Crafts acylation, which is the approach we're going to take here. So there's our acyl group. And in this case, with, temporarily, he is a meta director. And so if I want to add an electrophile meta, I could do it now before I reduce that with either the Clemmensen or Wolff-Kishner reductions. And so that's what we need to do. We need that bromine to be meta. And so the time to act is now with our EAS reaction. And whether we choose this meta or this meta, it is exactly the same thing, regardless of how you draw it due to symmetry. And finally, we need to do a side chain reduction. And again, we could do the Clemmensen or the Wolff-Kishner, and I'll just choose the Clemmensen here. Truth be told, in this example, they'd be interchangeable. And there indeed is our synthesis. So last example here, and we've got, again, benzene, and we're still trying to produce a disubstituted benzene, and we'll take the same approach here. And so we'll say if we attach the bromine first, well, where would he direct the next electrophile to go? Well, he's an ortho para-director, and that's not where we want the next substituent to be. Okay, so what if we add the amino group first? So what kind of director is he? Well, he's also an ortho para-director, and so we've got ortho and para, and so he's not necessarily going to direct this in the right place. Now, we could be like, well, what if we do the Br2-FeBr3 and use the Lewis acid and get him in the right place? That actually is a possibility, but probably not the route your professor was anticipating, but you should get full credit if you go that route. So, however, we're going to take a different approach and just say, well, neither one of these worked, which means we're looking for one of those crossover reactions again. And if you recall, one of the crossover reactions we looked at was actually doing a nitration followed by reduction to the amine here. And so if we look, how do we get that amine on there anyways? Well, again, we've got one major way to get the bromine on there. EAS bromination, Br2-FeBr3. So, but to get the amine group, we actually have a couple of options. So one, we could do nitration followed by, nitro reduction. But two, if we had a good leaving group here, like a bromine or a chlorine, we could actually attach this with an NAS reaction. Problem is, to get two halogens meta to each other is not the easiest thing in the world. It is possible, but not with the set of reactions we've presented in this chapter. So in this case, we're probably going to do nitration followed by reduction, which was one of our crossover reactions. So there's our nitro group. And again, what's nice is that nitro group being electron withdrawing is a meta director, but once I convert it to the amine, it'll be an ortho para director. And so I have a choice. Do I want to do EAS before or after that reduction? Well, definitely before, because I want a bromine to be meta to this position. And so before we do the reduction, definitely doing bromination. Cool, and then all we've got to do now is reduce the nitro group, and we've got a couple of different options. We could do general reduction, like with H2 palladium on carbon, or we could do the specific reduction again, which is what I'll do. So Fe, HCl, followed by hydroxide to neutralize. And again, I could have used zinc, tin, or iron. I chose iron this time around. And there we go. That reduces the nitro group to the amine, and we've completed our synthesis. And I've thrown several tricky examples at you here involving some of these crossover reactions and stuff. I've shown you examples where you got to make sure you do the Friedel-Crafts before you add a deactivating group like a nitro group. But in these 6 problems we've done, I've thrown some of the trickier examples I can think of at you so that you've seen them before you cover this on your exam. Now, if you found this lesson helpful, would you consider giving me a like and a share? Again, pretty much the best thing you can do to make sure other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you're looking for EAS practice problems, if you're looking for a final exam rapid review or a practice final exam at the end of the semester, check out my premium course on chadsprep.com.